All right, now let's talk a bit about metal preferences for how quickly chemical reactions happen with these transition metal complexes. The 1983 Nobel Prize was for Henry Taubé's work on mechanisms um, for electron transfer at metal complexes. And he also was the person that worked out how the DN electron configuration affects the rate of ligand exchange. So ligand substitution reaction we have here, uh, this is what we talked about before. Ligand X is replaced by ligand Y, where X is the leaving group and Y is the entering group. Taubé defined some terms. So a labile ligand, so a ligand that's easily lost, will, at a concentration of 0.1 molar of the complex, has a half-life of less than 1 minute. So labile means easily lost. An inert complex will, at a concentration of 0.1 molar, has a half-life greater than a minute. So labile is relatively easily lost, and inert is more difficult to lose. The half-life, of course, being the amount of time that it takes for the concentration to decrease to half of its initial value. Labile and inert are kinetic terms. They refer to how quickly a reaction happens, how quickly we are, in this case, exchanging ligands at the metal center. And you need to note that this is different than stable and unstable, which are thermodynamic terms, which tell us whether the reaction will be exothermic or endothermic. All right, the terms inert and labile are kinetic terms, and that means that they are giving us some idea about the activation energy. And in this case, it's the activation energy that we need to go over in order to break a bond to the metal center. And so for this Ml6 complex, the amount of energy we need to put in to turn it into Ml5 plus L. Okay, so rate determining steps of slow reactions have high activation energy. So if this activation energy is large, reaction will be slow. Okay, so a labile complex will have a small activation energy, and an inert complex will have a large activation energy. Well, the nice thing was Taubé was able to work out how the electron configuration gives us a guide to this. So large delta G double dagger, so slow reactions or inert metal ions are those with a large crystal field stabilization energy. So D3, low spin D4, low spin D5, low spin D6, and D8 all tend to be inert complexes. They undergo ligand substitution very slowly. Whereas the remainder, and I won't go through and read them, the remainder of the electron configurations are fast reactions. They are labile. Okay, and again, don't get this confused with thermodynamic terms where stable means that delta G is greater than 0. So stable means that the reactants are at a lower energy than the products, and unstable means that the reactants are at a higher energy than the products. All right, let's look at a couple examples of this. So we have for this particular reaction, this is cobalt-3 with 6 ammonia ligands reacting with 6 equivalents of H3O plus, which we would get by adding acid to water. It's 6 equivalents of hydronium to give us 6 waters attached to the cobalt center and 6 ammonium cations out of this. So this hexaamine cobalt-3 center is unstable toward reaction with acid, but this reaction takes several days to proceed even with relatively concentrated HCl. That's because the cobalt hexaamine complex is inert under these conditions. So it is unstable thermodynamically, meaning that this is an exothermic reaction but inert. Well, what makes it inert? The ammonias must detach from the cobalt center in order to get protonated. But the protonation is a favorable thing to happen once they're detached. And so we're waiting for the kinetics of the reaction. We're waiting for these ligands to be released one at a time in order to be protonated. But once they're protonated, they react very quickly. The rate determining step here is them detaching from the metal center. Whereas we have nickel 2 reacting with 4 cyanides to form this nickel 2 tetracyanonickel 2 complex. Here the exchange occurs very rapidly. So we can take and form this complex, and we can add in labeled cyanide. And when we do this, the label scrambles into these sites essentially instantly. By the time we can look by any sort of spectroscopy, the labeled cyanide has made it in there. Well, this reaction is actually isothermal. So the two reactants and the two products have the same energy, so there's no exothermicity or endothermicity that happens here. It's exactly the same energy. So it's thermodynamically stable, but it is labile. So these ligands are falling off and reattaching over and over and over again. And so this is a stable reactant, but is also a labile reactant. All right, here's the kinds of things that you'll want to be able to sketch. So, and this is pieces of one of those reaction coordinate diagrams for inert and labile complexes. So, in this first one, it is exothermic. And how do I know that it's exothermic? The products lie at a lower energy than the reactant. So it's exothermic. The reactants are unstable with respect to the products. However, this is a large activation energy. The EA value is large, and so this is a slow reaction. All right, and then we have more detail in B here. So this is again an exothermic reaction because the products are more stable than the reactants. We have a large activation energy, so this is a slow reaction. And this one, however, has an intermediate. So we have a valley here at the top of the mountain. So there should be a stable intermediate there that we could potentially observe. And then finally, in C here, it is endothermic reaction. So the products are at a higher energy than the reactants. So this reactant is stable. However, there is a small activation energy. So this EA value is small, and so traveling up to the products doesn't require very much energy. Okay, so it's a fast reaction.